Hello everyone, I'm going to talk about chapters 21, 22, 23, and 24. We are focusing, at this point, we're focusing on the topic of regression analysis and modeling using regression formula. And the topic that we will focus on today will, in fact, include simple regression model. We will talk about some conditions of simple regression model, and after that I'll talk about multiple regression and conditions. So this will be in multiple steps, multiple videos and sessions. So let's start with the basic of simple regression model. And you can see that here we have an example. So this is number of units. So we're producing and selling some units of production, and we have production time. So how long it takes for us to produce and sell them. So the main idea here in this example from the book on chapter 21 is talking about a linear regression model and understanding, in fact, the basic statistics of linear regression model. We're going more into details of statistical and mathematical basics of regression model, and we're going to understand how to know that a model is reliable, and can we use that model to make a decision or not. So again, not every regression model that we create are reliable. Not all of them are reliable enough so you can make a decision based on those regression models. So in this case, the first thing I see here in this scatter plot is that we have a linear shape, right? The scatter plot looks like a line. And what else do I see? I see that the fit line is going through the data, so that's very important. The fit line needs to go through the data, and there must be approximately equal amount of points and data below the line and top of the line everywhere. We don't have too much up and downs. Approximately in average they are spread around the line. So this is showing we have low variation in data. If there is a high variation, what happens? Some of these are very far from the line, some are very close to the line, and that's not helping us with our decision making. So in this case, you can see that on the left hand side of the equation, so this is the regression equation. On the left hand side of the regression equation, we have estimated production time. So I want to remind you that the value of dependent variable or response variable, it's always an estimation. It's always an estimation. It's not exact. Why is it estimation? Because we're using the formula for the line, right? And the formula for the line, not all of those points, we don't see all of those points to be on the line. If all of the points are exactly on the line, no distance, that's a model with zero error. But in this case, and in most cases of regression analysis, we're going to have many points. They're far from, they have a distance from the line. Distance of each point from the line is considered as an error. Distance of each point from the line is considered as an error, and this error, we also call it residual. So for example, this distance is E1, E2, E3. So if you have 100 data, we have E1, E2, E3. These are all the sum of squares of all of these errors create the total error. So what's the goal in regression analysis? We want to minimize the sum of these errors. And in fact, you can actually create millions of different lines next to each other going through the data and represent this relation or association, but only one of them, which is a regression model, has the minimum distance from all of these points, and that's a regression line. So again, this is an estimation because of the error that exists in calculation of the line. So this line is in fact an average. In average, we are calculating where these points are directing, right? Where are they going? Where are they moving? And then we can use it to make more calculations. So for example, where do we get this data? This data are coming from past information, past sales, past productions. So in the past, we had cases that we had like 90 productions, and it took us, for example, 200 hours. We had maybe 500 productions at different, one time it took us 810, another time it took us 300, right? 300, one time 800, one time 1000 hours to make or produce the 300 products. And same goes with the 500. But there are cases that we don't know. For example, if we say 400 for example, or 390 falls here, we don't have any data on it. How do we calculate, and how do we promise to our customers or clients that how long it's going to take for us to produce what they order? So their order is 390. We have not experienced that before. We don't know how long it's going to take, but we need to promise them a certain time and deliver that promise, right? So what do? We come up with a regression model, regression line like this. We come up with this equation. The number of units that we want to produce, we put it here in, we can have an estimation of the time it's going to take for us to create or produce those products and deliver it. So in fact, this is going to help us in decision making and helping our clients or customers in understanding that the amount they are ordering, how long later in average they're going to get, or what's the estimation of time that they can receive the production. And they can count on it. They can schedule their plans and make sure the project is complete after delivery. So again, this is an estimation. Remember, response variable is estimation, but number of units is actual. We give actual values for number of units, we get an estimation for the DV. So again, we're trying to calculate, we're trying to estimate the DV using different values for IV. And how do we do that? We create a regression model using the past data. Okay, so simple regression model, we all know what it is. So I want you to be familiar with this, representation of regression model. So I said regression model is estimation. So what is mu? Mu represents average. So in average, we're calculating y. In average, we're calculating y for a given value of x. Average or estimation or mean of y values for a given value of x. And that's E stands for expected value of y. Again, we are talking about estimation, right? Expected value of y given x is equal to a certain amount of x. And this calculation, so this is your regression model, this is your regression equation. You have intercept, you have slope, you have IV. Intercept, slope, IV. So beta 0 or B0 plus B1 or beta 1 times x creates the estimated value for the DV. So what are the conditions here for the regression model to be a good model? We'll go through a lot of information, but we'll go slowly and one by one. So one of the things we have here is deviation of response around mu. So what is deviation? The best way to remember deviation is standard deviation. standard deviation, and variance. What do they show? They show variation. And variation means how the data are spread around the mean. And we spoke about that. If the data are close to the mean, when you make a decision based on the average, it's going to work for majority of your data or your respondents. If the data spread is very far or has a high variation from the mean, when you make a decision for the mean, a small portion around the mean, your decision is going to work for it, but those that are far, they're not going to work. So one of the things that in a simple regression model we're looking for is a low value of standard deviation or variance or variation. Another thing is the errors. So I told you that we want the regression line goes through the data. Means you have approximately equal amount of points on top and below the line. You want to have approximately equal amount of points on top and below the line. And if that happens, those points that are on top of the line, they're positive. Those on below the line, they're negative. The average of them, or expected value in probability, is actually average. So in average, these epsilons or these errors are going to cancel each other, and in average they're going to be 0. This is not exact 0, it's going to be close to 0. So in average your error has to be 0. And how does that happen? When you have that you have such scatter plot. So those below the line are negative, those top of the line are positive. If they are spread around the line symmetrically and with the low variation, then in average they're going to have average error of 0. Okay, so these are two things that you just learned. And then what else do we have here? We have normality of errors. So we want the errors to be normally distributed. We want errors to be normally distributed. What does it mean when we say something is normally distributed? A normal distribution looks like a bell shape. The center of the bell is average. And that bell shape is telling us majority of data are around the average, right? It's the same here. If our errors are normally distributed, majority of them are close to the average error. And that average error is actually the line, right? So we can say that we have most of the values or errors close to the line, right? Another thing, we want to have approximately equal variances. Equal variances. What does it mean, equal variance? What is variance? Variance represents variation. Going back to this scatter plot right here, look, the variation, the changes of x values. One of the ways to calculate variation is range. The highest minus lowest, the highest minus lowest. They are approximately in the same range. So if you put a line on top here and put a line on the bottom here, they are in a certain range. So there's not too much variation around. So what does a too much variation looks like? It looks like this, go up and down, up and down, up and down. Or one side is completely close, another side is completely far from the line, and it creates like a triangle, right? So this actually looks good. It has low variation. So the variation is similar around. The variation is similar. So we want equal variances or similar variances around the regression line, right? All errors have the same variance. And then independence or independent. We want errors to be independent. Errors should be independent of each other. What does that mean? If errors are independent, that means they are randomly spread everywhere around the line. that means your points, your data are spread around the line randomly. So if these errors are actually dependent, that means something is wrong. So for example, in that scatter plot, if a part of your data are completely below the line, a part are completely on top of the line. Especially in curve relations, this happens. So this want to tell us, this is going to help us to understand if is our regression line going through the data, and do we have data everywhere around it, or all of the data are just focused on one side, and on the other side we just have few points very far. So this is not something we are looking for. So remember these three are actually very important in regression analysis. These are not all the conditions we are looking for, but they're actually the main ones that you need to remember. So if you want a regression model, simple regression model, to be reliable, the first three conditions, we also call them assumptions, conditions or assumptions of regression model is, and this is about the residuals or errors, right? Epsilon. They're supposed to be independent, meaning that if we get a correlation between them, among them, the correlation is 0. Equal variances, so the changes or range or standard deviation around the line is the same, it's not changing too much. And they follow a normal probability distribution, means majority of them are supposed to be close to the line. Alright, then let's see what else we have here. Okay. So write them somewhere, make sure you remember these three. We're going to need this until end of semester. We're going to repeat this, and we're going to need it. Every time we find a model, we check these three at least. There are other conditions that will be added later. Okay, data generation. So here we created a model, and why do we need a normally distributed data, right? You can see if your data are following a normal distribution, it's easy to predict and say what's the shape of the next level of data. If you want to produce, let's say this is 200 production, you want to produce 300, you can approximately, and with a high level of accuracy, you can calculate and say what is the shape of the next level, right? But if they're not following normal distribution, then these are not the same. They're going to change a lot, and that means high variation. High variation means you have lower accuracy in your calculations. So let's move down here to, okay, so I told you the left hand side, or the response variable or a dependent variable, is an estimation, right? Why is that an estimation? Because errors are involved. Now if we add error on both sides, the left hand side, instead of being estimation, will become exact. So y represent exact value for dependent variable, and what is added to the right hand side? We added the error. So if error is gone, right, if error is actually being calculated in our calculations, then we can say that we have exact and accurate results. And I just want to make sure you understand this notation here. This epsilon represents error. This means it follows. That's tilde. Tilde here means it follows. N means normal distribution. Normal distribution. So errors, they follow normal distribution with 0 average and variance of sigma square of epsilon. So this is actually telling us the three conditions we were looking for. This is actually showing the three conditions we were looking for, right? Epsilon follows a normal distribution, so they are independent. Average is 0. Standard deviation or variance is sigma square. So observations are independent, have equal variances, that's sigma square, and they are normally distributed, and that's n with the average of 0. Cool, huh? Okay, checklist. Conditions for simple regression model. Again, there are other conditions that I will add later. Is the association between y and x linear? How do we check that? Scatter plot. We create a scatter plot, calculate the correlation value, look at the p-value. Is that linear? Have we ruled out lurking variables? There are variables that we probably did not get data for, or we did not take it into calculation. There are variables that we did not take into calculation. Okay, and those variables, they could actually have effect on both or one of the IV or DV, and this influence is high enough that if you include that variable, results are going to change. As an example, let's say I'm doing a study on a student's grade as a DV and a student's attendance as IV, as independent variable or explanatory variable. So I come up with a regression model, but one of the students raise hand and says, so maybe we all attended class, but there are other factors involved in the calculation, and professor, you didn't take them into account. Can anyone help me understand what those factors could be? Other than your grade is influenced by attending class, is there any other and highly correlated or highly effective factor?
Like study time.
Study time, yes, study time, right? We can also add attention in class, right? You might attend class but don't pay attention. So the time you spend at home on practicing, on studying. So that could be a lurking variable, and we can check it. I want to remind you that for this semester, I'm not spending that much time. I'm not never asking you to find the lurking variable. We have case studies. You can read it from the book and understand them. But again, the example I just told you, I think that's the best example to remember what lurking variable is. Okay. Are the errors evidently independent? All right, I'm going to show you how to know the errors are independent. So we need to make sure that they are not following a certain pattern. They are all around the error line. Are the variances of the residuals similar? Are the residuals nearly normal? So these are the questions we ask. We want to make sure that a regression line is a good regression line, and we can use it, and it's reliable to make decisions. So this scatter that you see is not a scatter plot. This is in fact the residuals plot. This is the residuals plot. What are residuals? Residuals are errors, right? So we put the 0 error on that horizontal line, the red line, do you see it in the middle? That line, that horizontal line is residual of 0. It means the points that are exactly on the line. So the rest of the points are how far they are from the regression line. And if you see it here, they are randomly spread around the line. And we have equal amount on top and bottom of the line. They don't have a pattern. They don't create a line moving up or moving down. So if they look like a rectangle around the error line, 0 line, or like a circle, symmetrical around the line, right? Around that horizontal line, red line, that means we have independent residuals. If they are not independent, you will see like a pattern here. They're going to move up or move down, or look like a U, or look like A, and so on, or look like a V. So linearity is satisfied. We don't see any patterns here, and similar variances are satisfied. How do we know? similar variances are satisfied here. Look from left to right. If I just ignore that one point, all of them are almost with the same range, right? Same range, same range. The differences or the variances or the variation of data from one place to the other place is not changing that much. One of the signs is that the graph looks like a rectangle or a circle. But how do I know if it's not similar variances? It might look like a triangle. On one side they're all close to this zero line. On one side they are very far from the line. So it looks like a triangle. That would be a case with the non-similar variances, and also with the pattern. Okay, so how do we check normality of residuals? How do we check normality of residuals? There is a plot on distribution. You remember distribution on JUMP, it actually creates for you the box plot, histogram, mean, median, mode, standard deviation, right? It also creates a normal distribution around, we call it a QQ plot or normal quantile plot around residuals. And if residuals, they all fall between the upper bound and lower bound, that means residuals are in control or residuals are normally distributed. And you can see that majority of them, and how is this histogram created? These are distances from the center, from zero, right? Are they very far from zero, or they're all around zero? So you can see in this case, they're all very close to the line, and it's normally distributed. Okay. Later, other than this chart, later I'm going to teach you another method, statistically, with a hypothesis testing, with the exact value of p-value, we can actually say this data is normal or not, because sometimes looking at the graph, you can have an opinion, and I can have a different opinion, and I don't want to talk about opinions, I want to be exact. So later I'm going to teach you a method, which that method is going to teach you how to exactly say the data is normal or not, the residuals are normal or not. Okay, modeling process. So before looking at plots, ask two questions. Does a linear relation make sense? So please watch the videos for chapter 19 and chapter 20. That's going to help you to understand that part. We have actually already talked about this in the previous session, so I don't want to go through that one more time. Is there a relation free of lurking variable? So always make sure, is there another factor influencing on your IV and DV that you're not counting it, taking it into account? Then begin working on your data, and always check those conditions that I said. Remember, for the data, we name, this is just notation, okay? For data, intercept is represented by B0. Simple regression model is represented by beta 0. Slope is represented by B1. On regression model, we represent by beta 1. The line, the regression line, by y hat, but in regression model is an estimation, so we show it with the mean or mu of y given for a given value of x. Deviation or errors by e. Errors, simple regression model, we show it on using an epsilon. Standard deviation or standard error, we show it with the SE. This is a standard error. SE is a standard error. SD of epsilon is standard deviation of errors. So we have errors, and we can calculate the standard deviation of them. Right? So on SRM, we show it with the sigma of epsilon. On data, we show it using SE. So when you read the book on chapter 21, especially 21, 22, 23, 24, when you see SE or sigma of epsilon, they represent standard error. And standard error is standard deviation of errors or residuals. Okay. those distances from the line. Okay, so the next step is the standard errors. So describe the sample-to-sample variability of B0 and B1. So estimated standard error of B1 is standard error. And again, what is a standard error? Standard error is standard deviation of residuals or errors. Divide by radical n minus 1 multiplied by 1 divided by Sx. What is Sx? Sx is standard deviation of independent variables, values. And that's approximately equal to standard error divided by radical n times 1 divided by standard deviation of x values. So what this is telling us, for B1, the standard error or standard deviation of errors for slope is actually has inverse relation with the sample size. That means if you have a large sample size, right? If you have a large sample size, you will have a lower standard error. Lower standard error means your errors are all small, or majority of them are very small values. And small value of standard error means you have low variation. Low variation is good, right? It helps us to have a better estimation for our results. Also, standard deviation of x values or IVs. If you have a larger standard error, standard deviation of x values, what is standard deviation for? Standard deviation, I want you to write this somewhere really large with a different color, put some stars around it. Standard deviation represents variation. Write down the word variation really large enough so you always see it. Standard deviation represents variation or equals to variation, is a factor of variation. So same as sample size n, if standard deviation of variation of x values is large, that creates a better model. That means you have lower standard error for slope. And why is that? So we can look at this these two plots here, and here we have a low standard error of standard deviation of x values. It means x values are just between 4 and 6. So they're not high in variation. There's not too much difference between these data. They're between 4 to 6. But if we look at the left-hand side plot, you can see that the left-hand side plot, in fact, has a high variation from somewhere around half up to 10. This is a high variation, and it creates better model, better accuracy, because you can see here there are many other models or lines that can predict the same relation, but here they can be different, but they're actually showing the same thing. These are different. So there's a high variation in results, less variation in results. So you can similar results here, and that's a better and a higher accurate modeling. This is an example of inference. Inference means hypothesis testing, right? You remember inferential statistics is generalizing for statistics, for results. So decision making for a larger population or sample. So these are the results, R-square. You remember R-square. You remember the sample size from the results. But what you don't remember and we never talked about was a standard error. Now you know what a standard error is. A standard error is standard deviation of errors or residuals, 119. Intercept, that's your estimation for intercept. That's your estimation for the slope. So intercept and slope. And these are the standard errors for slope and the intercept. And these are the p-values. So other than the p-value that should be below 0.05, there is another method that we can use, and that's calculating the confidence interval around the intercept, around the slope. So 95% confidence interval for beta 1 is the slope, right? Slope of the regression model is B1 plus minus, that's a t-distribution, you learned it in Stat 1 or Basic Statistics, multiplied by standard error of B. And if you want to remember this very nicely and don't feel confused by the numbers and the way it's represented, it seems complicated, but it's actually not. So we are estimating the average, the slope, right? So that's your average plus minus 2 times a standard deviation, approximately 2 times a standard deviation covers 95%. Do you remember that from standard deviation? That's the same thing. 2 times of standard deviation around mean covers 95%. That's the same thing. And 3 times a standard deviation around mean covers 99.7%, approximately, right? So looking at the current data, we calculated that t-value, and it's actually 2.014. It's close to the 2 that we said. It's 95%. Will I ask you to find this number? No, I won't, right? But if you remember from Basic Statistics, you need to go to the t-table and look for 95% two-tail. 95% two-tail on the t-stat table, you can find this number. This amount of a standard error, a standard deviation of errors around slope creates that interval. That is the interval of 95% of our data in that range. And same thing for B0 or the intercept. We also can create that interval. I'm going to show you on JUMP how to calculate these numbers. You will never have to calculate it yourself. You can use JUMP. With a few clicks, you can get those numbers out. And what is the hypothesis test on this? Hypothesis test will be, of course, we want to have a positive or a negative, a non-zero intercept, a non-zero slope. If one of them is 0, we don't have a regression line, right? If the slope is 0, you don't have a regression line. If the intercept is 0, you don't have a regression line. So the hypothesis null will be beta 1 or beta 0 are 0. Means intercept or slope is 0. And what are we about to do? We want to reject HO. We want to say if the regression line is reliable, we will reject HO. How do you know the regression line is reliable? We look at the p-value. In this table, you see in the p-value on the right hand side. If p-value is below 0.05, we reject HO. That means the intercept and slope are not 0. They are actually numbers that are reliable. Okay, so what is this saying? Saying, okay, the test statistics of 16, p-value is below 0.05, indicates that the slope is significantly different from 0. Rejected HO. Same thing with the intercept, right? So we can reject HO for both. That means beta 0, beta 1 are non-zero. They are actually some numbers. So we did this. If 0 lies outside the 95% confidence interval, is another way to recognize that you can reject HO. So in this case, that we calculated the upper bound and lower bound, is 0 in that range? Do you see 0 in that range? The answer is no. So reject HO. Is 0 in this range? No. So reject HO. So they are supposed to be both negative or both positive. Both negative or both positive. That means reject HO. So if p-value is not given to you, and instead you have interval, the confidence intervals, how do you know? You must make sure that 0 is not in that range. If 0 is not in that range, we reject HO. Okay, so a lot of information, right? So chapter 21 to 24 is actually, you're gonna get a lot of information, new information that you probably didn't know before. All right, so the rest is just another example, and I just want you to read the book on this topic. These are exactly the same thing we did today. So what I'm going to do, I'm going to show you on jump how to find these numbers and how to interpret them. So let's open, of course we have one, in this case we have one IV1 dV, so fit y by x, and we go for, let's go for profit, and let's go for maybe number of employees. So that's our example. We want to see the influence, or we want to see the association of number of employees and profit. So click OK. Well, so let's see what we can do here. Bivariate fit. So let's see the fit line here. That's the fit line. So what's the first thing you learn to do when you have these results? Looking at the scatter plot, we're looking for the data to be almost everywhere around. But you can see at the beginning, we have a few data, some of data are concentrated down here, but on top we have just 3. Another thing we look at is the range here, or the variation at the beginning is low. We move to the right hand side, we have a higher variation, higher variation, higher variation, right? So something's wrong with this model. Probably by removing a few more, this 3. If I remove this 3, the regression line will move a little more to top and will be much better. But one of the reasons we don't have a very nice equation or regression line here is because we have 20, I think here we have 29 data. Remember that I told you we divide by radical n, right? The higher the sample size, the lower the standard error, and lower standard error means a better fit. What is the R-square? That's another sign here, 12%. What is a good R-square for us? More than 50%, more than 0.5. And more than 0.5 means the correlation is more than 75%. So that's a good, strong relation. So that's what we are looking for. What else are we looking for here based on what you learned today? Look at the intercept, the parameter estimates table. Intercept is the p-value below 0.05. So we cannot reject that as well. Is the number of employees has a p-value below 0.05? No. Can I find the confidence interval here? Let's try. I right click on the table, I right click on that parameter estimates table and go to column. I want to add a new column, and that new column for me is lower 95 and one more time upper 95. So I have lower and upper bound around the estimate values. Did you see that? You don't need to use that formula, difficult formula to calculate. You can simply get the lower and upper bound around this one. And what is this number? This is your t multiplied by the standard error added and subtracted from 133. Your t value added and subtracted from your estimate values. Okay, what did we miss here? We missed to calculate or find the values of error. So to do that, I hope jump is doing it the same as before. So I click on that red triangle over line fit and I try to find residuals. Do you see residuals here? Do you see it? Save residuals. So I click on save residuals. Residuals are being saved on the actual data at the end. One more time, I click on the red triangle of linear fit, click on save residuals, and where are they saved? They're saved at the end of my data. Now I need to see if they follow normal distribution. Are they having a mean of 0? Are they having similar variances and normality? So I go to Analyze and Distribution, and simply just drag and drop residual profit. This is the residual of profit, and drag it into Y column and find the histogram and all the things that I needed. Alright, so I want to see this much better now. I make the histogram like that, vertical. And what else do I need? I want to see normality of, see the normality of residuals. These are the results of residuals, right? So let's go here. And normal quantile plot, right there. Red triangle, normal quantile plot. Click. Do you remember the shape I showed you on the book? So you can simply just create that. And we hope that less than 5% of this point are outside that range. In this case, I can see 1, 2. This one is on the line, so 1, 2, 3 out of 29. 3 out of 29, if you calculate, is that less than 5%? That's how you calculate. Okay. There are other ways to know. So, is this normal? I believe this is not normally distributed. You can see that they have a pattern here. Right? They have a pattern to go out of the control system. Okay, what else do I look at? Go down here and look at a standard error. So what is a standard error? Standard deviation of errors, right? Standard deviation of errors is very high, 434. It's a large number. You don't expect to have that much large number. What's the average of errors? There's the times 10 to the power negative 14, which means it's very low. So that's close to 0. That's actually 0. So we don't have to think about that. What else should I check? There's another thing I should check, and that's the residual scatter plot. The residual scatter plot is not here, so I'm going to create it by going to fit y by x. My dv is, instead of profit, right, I'm going to use the residuals of profit. Again, let me explain it and write it down. What am I creating? I'm creating a residuals plot. Residual plot is the one with the vertical line in the middle, right? That data are spread around it. And what do I get for the IV? IV is the actual IV, which is number of employees. You do this, you can create a residual plot. Click OK. And that's your residual plot. You want a fit line? It has to be a horizontal line right there, which it is. Now, does this look like a rectangle? Data are spread around the line? No. Does this look like a triangle? Yes, this is like a triangle. On the left hand side, low variation, higher variation. Do you see that? So that shows a problem here. That shows that we don't have. And the quantile plot also confirms we don't have normally distributed data. So this model that we created is actually not reliable, and we also confirmed that by looking at the p-values of the actual regression that we created. It showed that this one wasn't this one. Let me find it. This one. This one, if you see intercept and number of employees, have a p-value more than 0.05. We fail to reject HO. Also, 0 is in the range of the confidence interval. They all are telling us that this is not a reliable model. This is not a reliable model. Later, I will talk to you and help you to understand how to change this and make a reliable model by removing some outliers. Sometimes it works, sometimes it doesn't work. In this case, I believe it works if we remove 28, 26, and 15. Okay, it should work because these are the ones that are creating too much variation here. Okay, so let me